Hello everyone, my name is Nam Nguyen, a PhD. I'm a senior data scientist from Schlumberger. Today I will talk about stack regressions for prediction tests. This is the agenda of the talk. First, I give a brief introduction about machine learning and regression in general. Then the motivation to improve the models through three approaches: bagging, boosting, and stack regressions. At the end, I do the performance analysis between the three approaches and draw the conclusion at the end. So machine learning can be divided into four branches, generally speaking. Unsupervised learning is where you don't have any label and you try to do the clustering. Semi-supervised learning is where you have just partial labels. So you don't have labels for the whole data set, but you just have a label for a subset of the data set. So you train the model based on the labels that you have and you do the prediction for the rest. And then you keep growing your labels. The third one is the reinforcement learning, where you have an agent to interact with an environment, and once it interacts with the environment, it measures the responses from the environment, and based on the response, it can see that what is the reward if it do a good job, what is its reward if it does a bad job, what is the punishment, and based on the punishment and the reward, it can optimize the action. It can choose the best action to control the environment. And the last one, and the most common machine learning, is a supervised learning, where you basically have two things: classification or regression. The main difference between the two is from the cost function. For classification, normally it's a cost entropy, and for regression, we're just trying to um, maximize to minimize the mean square error. So in the simplest form, regression is simply y equal to ax plus b, where y is the response and x are the explanatory variables. So you try to find a and b so that you can predict value y prime that is as close as possible to the real response y. So the assumptions have to be made for the linear regression to work. First one is, of course, linear dependencies. You have to have the linear dependency between the explanatory variables and the real response. The second one is that there must be no autocorrelation in the residuals. So basically the residuals, which is y minus y prime, has to be white noise. So if you shift the residual, you have a shifted version of the residual, and you find the correlation between that shifted version with the residual itself, you shouldn't find any correlation between them. And also it has to have a zero mean and equal variance, meaning that the variance is consistent across the range of the response output y. So doesn't the variance of the residuals doesn't depend on the range of y. No matter if y is small or big or in the middle, the variance should be always consistent and almost the same. That's it about the introduction. Now we know that there are a lot of regression models out there, and for a nonlinear task like this shown on the picture on the right, where we're trying to do a classification model, we can see that the green line is the overfit, is a boundary that generated from a model that try its best to overfit the data, so that you can see that every single dot on the left hand side of the green line, the red dot, and then all the blue dots are on the right hand side of the green line. So if you test on this dataset, the chaining dataset is going to work perfectly, 100% classification result. However, it has a big troubles if you try to test it with data outside of the chaining, because it is not generalized. So if you have a test dataset outside of this, it's going to perform worse much worse. So that is the motivation, like how we can combine different weak learners to form a much better learner. And the first that we talk about is the bagging technique. And one of the most famous implementation of bagging is a random forest, which combines a lot of decision trees together and produce a reasonable good result. So the main principle that it averages the model results coming from different models. And you have to notice that averaging the result does not mean averaging the performance. Okay, so what it means that it averaged the response of prediction values generated by model 1, 2 until n. Okay, so basically you when you generate those values, you come up with a model which has accuracy much better than the individual accuracy from a single models. So next slide, we're going to talk about why averaging multiple weak learners would give you a better result. This sounds a bit strange at first because if you think about it, you average some weak learner, how can you get a stronger learner? Because you are average something that is weak. Are you supposed to get something is also weak? The answer is no. So if you look at the figure on the right, you see multiple curves here. Each curve is overfitting the data, trying its best to classify the blue dots from the red dots. Now, if you do the average on those high variance models, you're gonna get the black curve in the middle right here, which is which has much lower variance. And because of this, you can reduce the variance from the other learners, and it can generalize much better with the testing dataset. So the key thing to remember is that bagging is that everything is calculated in parallel. All the models calculate and change in parallel, and then we can average out the output data, and it mainly used to reduce the variance of the model. The next thing is after bagging is the boosting, and specifically in this one I'm going to talk about the gradient boosting. Two of the most famous gradient boosting libraries out there is the LightGBM and HGB. So how it works? The main principle that they're different from the bagging, and this gradient boosting is stacking multiple models on top of each other. Each model is going to try to fix the error made by the previous model. And it is very similar. It has a very similar idea to gradient descent, where in each step you're trying to reduce the error so that you can converge to the local minima sequentially. So this is how it works intuitively. You have the number of layers at the x-axis. You have the real measurements here. So the first one is just like a shot in the dark, and you try to just to come up with a value. You can see the predicted value is much different from the real measurements. So with that, you have the accumulated predicted value in green. And since it is the zero step, there's nothing before that. The accumulated value is simply just the predicted value at step 0. And with this result, you generate this much of error, the difference between the yellow line and the real measurements. Now, at the second step, we bring over that value that we predict from the previous step, and we try to match the error that generated from the previous step. So this is the value that we generated. We use the model, the second layer, to predict. So the yellow line here, we try to match that yellow line with the red line, the absolute value of the red line. So notice that it is the positive, but it is negative. Now, if you add this negative value to the previous value that you predicted at step 0, you're gonna have something that is closer to the real measurements. Yep. So this is the accumulated value that we predict at this step 1. Still at this step, we generate some errors, which is the red bar right here. And we still need to run a few more layers to reduce this error. Similar thing here happens, and this second layer trying to match the error generated by the first layer. And if you add this yellow line with the line right here, with the bar right here, you come up with something that is very close to real measurements, and the error was much reduced. So as you can see, from the 0 step to the first step to the second step, the error terms keep reducing until it's reached the real measurements. So that is the main principle about the gradient boosting. And now finally, I will talk about the stack regression, which is the king of all regression models. So in backing, we try to reduce the variance. In boosting, we try to reduce the bias. In stacking, we try to do both variance and bias. Well, this is win-win situation because normally you have to compromise variance with bias and vice versa. So is this magic? Let's dive in to see how it works intuitively. So this is the picture that I take from Farron from Kaggle. And you can see here there are two datasets, the training dataset and the testing dataset. There are two variants, A and B. In variant B, we use a k-fold. We divide the dataset into k-folds, and we leave out one. We train on k-1 folds, and we use that train model to predict the value for the leave out subdataset. And we use those prediction from all of the models here to form the new features for the meta model, model 6. So the second layer is model 6, and we normally call that meta model. This meta model will have the prediction value from model 1 to 5 here, and the corresponding value y as the response here, and it tried best to match the predictions to the predicted value. So based on that, the trained model from the meta model will be used will be applied on the test dataset to give you the prediction result, which is variant B right here. The second variant A, you actually use the model 1, the trained model 1 to predict the value for the test dataset, and you have the prediction from models 1 to 5, and then you just average all of those out to get the predictions for the test dataset. Now, generally speaking, in my personal experience, I normally achieve a better result with variant B, but variant A is already a big improvement compared to the single models. So we can try both and see how it works. Yeah, so this is the details, technical details, and you need to make sure that you using k-fold and you chain it on all the subdataset. You iterate through here, like you have 5 folds, you try to chain it on all the 5 folds. You chain it on 4 folds in each iteration and make the prediction for the leave out, and then you iterate. You choose another leave out and you chain on the rest k-1 folds and use a prediction on as a validation on the leave out dataset. So that is a key thing that you need to note. You need to that is very important, that you need to iterate and train through on the k-folds dataset. So intuitively, how the real question is why it works better than others. So think about this scenario on the figure on the right. You have three students here. The first one name is logistic regression, SVMs, and KNN. So now each of them have some input and they give different output. KNN's giving 11 while SVM giving 18 and RL giving 13. So now the teacher, which is Miss DL and Mr. RF, who is more knowledgeable, take all the input from all the students and they try to come up with a score with a value by themselves. So for example, Mr. DL knows that SVM normally performs really well. So she put more weight on SVM results and she come up with a number 17, while Mr. IF come up with number 16. So now there's a debate between the two teachers and the principal comes into the place and this is Mr. GBM and he said that, okay, based on the performance in the past of Mr. DL and Mr. IF, I will give the final result as 16.2, which means he believes that Mr. IF normally performs better than Mr. DL. So that's the main ideas. Each model has its own advantage, and the stack regressor gonna combine and take the advantage of each model. So for example, SVM performs really well in a certain data range, but it doesn't perform well in other data range. So, um, so what the Mr. GBM or DL or IF is doing is that it's trying to see the prediction value of SVM in those ranges and see if it performs the best in those ranges. And if it performs really well, then it's going to select, it's going to put more weight to the SVM result in those ranges of data. So that's the main idea. Each IL, LR, SVM, KNN, DL, RF has a strong performance in certain data input range, and by combining all the models together, Mr. GBM is going to be able to generate the best result by selecting the best models for each of the data range. So that's the main idea of stack regression, and now I'm gonna do the performance evaluation. So I take the source from a KD Nugget post, and the author trying to do the house price prediction from zero dataset provided by Kaggle. And you can see here the author built a model which has two layers. The first layer has the couple of models, XGBoost, neural net, and support vector regression. And the meta model, which is on the second layer, is built upon elastic net. And you can see that the stack regressor works defeats on the other individual regressor like XGBoost, neural net, and support vector regression. Now you can argue that you don't see much difference from 0.0 0.1000 versus 0.107. Now, this tiny difference is what makes the winner or loser in competition like Kaggle. So, yeah, so it's really important. It helps you to achieve the last few percentage of improvements that you want to make after you achieve like 95% accuracy. You may want to improve to 96%. Then this is the answer that you can look for. So with I'm gonna go to the conclude the presentation. I provided an overview of all regression techniques, backing, boosting, and stacking. Stack regression is a powerful tool that helps achieve the last few percentage of performance improvements. So stack regression actually started a long time ago, and it has been theoretically approved, and now it has been practically proved that it outperforms the other models in both regression and classification tasks. And the main idea of the stack regression is that it selects the best features from all the available single regression or classification models to combine and give the best performance model. Thank you for listening in, and I hope you have a good day. Thank you.